Remember we calculated the fractions of the leaching fractions and the associated electrical conductivity in each layer. So the upper layer was 1.5 decisiemens per meter. The second layer is 2.5 decisiemens per meter. Third layer is 4.3, and the last layer is 6.7. And probably wondering why I keep emphasizing this. It's because it's really important to validate your model that it's calculating what it's supposed to. And I kind of poo-pooed it when it wasn't working. But actually, it's very important to have a validated model. And so that code, that simple calculation, validated the fact that this model is correct, this daily model of salinity, because the top layer is 1.5, the second layer is 2.5, third layer is 4.3, and top layer is 6.7. So if you can start with a model that's like validated by something, you're way ahead. So now I feel confident that the model is doing what it's supposed to, and then I can worry about other little details. Okay. So we've gone over this a little bit before, but I just wanted to remind you of how this works. For each layer, we calculate the final salinity based on the infiltration coming in from the top. So this is the irrigation water times the EC of the irrigation water minus the salt that we're losing below. So this is the deep seepage, if you want to call it that, times the EC initial. And actually, yeah, EC initial. So it says EC2, but that means layer 2 and not not time 2. Okay. And then we add the EC initial plus delta Z plus theta initial. So that's the initial concentration that we had. And then we find the final concentration by dividing by delta Z times theta final plus the infiltration 2. And this is a little bit different from the book. I added the infill 2, but that's, if you add this, it makes sense because you're mixing this with the amount of water times the depth. And so that's what makes the results agree exactly with that previous calculation. So, so anyway, this is going to be our equation, both for salinity and nitrogen. And if we look at the code here, we can see that the numerator is all this. So I is the time, J is the layer. So J minus 1 would be the layer above. So for the first layer, that would be the irrigation water layer. And so on. So I's are times, J's are layers. And so you can see that the numerator's here, and then I divide by infill at IJ. So this would be layer J plus my initial amount of water, which was the layer thickness, DZ, times WC. Okay, and so today we're going to be emphasizing the actual ET, the actual evapotranspiration. Remember last time when we were just validating the model, we just said the evapotranspiration was 1 centimeter per day, which is a typical amount, but that's not realistic. And so now we're going to take the daily evapotranspiration that we got from the weather station last time. We're going to multiply that times the crop coefficient, which I'll talk about. And then that'll be our ET. So this would be the entire profile. And then for each layer, we're going to calculate the crop evapotranspiration for that layer, not for the entire profile, because we're calculating how much is leaving for each layer. And so that would, the total crop evapotranspiration would be the reference, this ETO is the reference evapotranspiration from the weather station times the crop coefficient. But then we have to multiply times another fraction because each layer has a fraction of the total evapotranspiration.
That is for the entire plant. The reference evapotranspiration is the whole thing.
The reference evapotranspiration is what you get from the weather station. So based on humidity, wind speed, solar radiation, they calculate that for you. And that's what we downloaded last time, Penman-Monteith. We downloaded, there was many different versions. So there's slightly different calculations, but we used the Penman-Monteith calculation. Okay, so then we're going to multiply that times our crop coefficient, and then we're going to get our fraction for each layer. And basically, right now we're saying it's 40%, 30%, 20%, and 10% for the 4 layers. So 40% of the ET is coming out of the upper layer, 30, 20, 10. But because we have root growth, we have to adjust that, because if the roots aren't in a layer, they're not going to take anything out. Okay, so here's the crop coefficient curve. I briefly presented it last time, but we have this initial phase, development phase, mid-season phase, late season phase, and end season phase. And so there's certain key numbers here that help us define this segmented curve. The period of the initial phase, the period of the development phase. So this is on this axis, the period of the mid-season phase, period of the late season, period of the end season, and then the crop coefficient values for each phase. So 0.4, and actually we only need 3, 0.4 for, well, in our example, it's going to be 0.7 because it's broccoli. But the initial crop coefficient, the mid-season crop coefficient, and the end season crop coefficient. Okay, so let's see here. So we have that in the tipping bucket crop page. And so I have I have this constant crop phase where I say the crop coefficient is always 1. So that way you can just evaluate the model, not worrying about what the crop is doing. But we have this broccoli crop phase here, 35, 45, 40, and 15. And actually, I'm not sure this is right, but I'm just a modeler. I don't care about reality. I think it's shorter. But anyway, for this model, we're using that. And then I did get these off FAO 56, the Food and Agriculture Organization 56. The initial is 0.7, and I think that's really high, but I think it's because they're sprinkling every day to germinate. So they're wasting a lot of water there. And then the mid-season phase is 0.95, and the end season phase is 0.85. And so you can see that here's the titles of the columns, and I read in these numbers, the initial phase, development phase, and mid-season phase, late season phase, end season phase. I read them in off the columns like that, and I read in the crop coefficients like that. And then I calculate the crop coefficient curve. If it's less than the initial phase days, then it's initial. If it's during the development phase, I have to have an interpolation function. So that's that. If it's less than the initial phase plus the development phase plus mid-season phase, so that's the mid-season phase, then I just say it's the mid-season crop coefficient. And then I have the end season or the late season phase where it's another interpolation function. And then yeah. So I calculated the broccoli crop coefficient, and it looks like I only calculated it for 100 days, and I should have calculated it longer. But anyway, who cares? We're just modeling, having fun. But the point is that it works, this calculation works. It would work for the end season phase. Here's my crop coefficients for broccoli. Here's my time after planting. And so if I put that crop coefficient into my model, so here you can see that my ET is my reference ET off the column in the daily phase or daily spreadsheet times my crop coefficient. So you can see that I'm taking out more water later in the season. Okay. So remember, these are each of the layers. Water content is on the y-axis. And so the upper layer is depleting more than the other layers. Upper layer is 0 depth. And because it's remember, its fraction of ET is 40% in the upper layer, then 30% in the next layer, and so on. So this is that fraction of ET here, 40, 30, 20, 10. I divided by 100. I'm going to change that. The new model doesn't have it exactly like that. Okay, any questions on that? Oh, and I'm irrigating every 3 days. That's why it's coming back up to 0. Okay, and so if you remember, we acquired our weather data in Posit Cloud. Were you all able to make that work somehow or another? Run the R program? Great. Okay. So the things I wanted, now you can just say what you want. I wanted date time. I wanted ETO, Penman, Monteith. I wanted precipitation. And although I didn't use it today, usually you want to use, you do want the temperature, the max and min temperature. So I got those daily values. I started on the day I planted broccoli. And so we just grew broccoli in an experiment this winter up at Maricopa. So we planted around October 10, October 1st. And I can't remember when they harvested. So I just took the data till March 1st. And it's weather station 6 because the experiment was at Maricopa. Okay, any questions on this? All right, and I changed the names of my columns because I didn't like those columns. And I also, because they gave me the data in millimeters in my models in meters, I multiplied them both by 0.001, the rain.
Is it referred to on just one?
Yes, 1. Okay, so here's my the new weather too, where here's my first date. I also added in a day of year column now because I needed that for my calculations. So this is a little bit out of date, but the tipping bucket spreadsheet that you have has a day of year column also. And I had to kind of do this manually. I didn't set it up so that well, this isn't manually. This is just off the Posit Cloud R program. But I had to transfer the data to my tipping bucket because it's not exactly in the same order. If you had time, I would put it in the same order so I could just copy the whole spreadsheet and be done with it. Okay, so here's my reference ET from the weather station. So you can see that October 1st, it's still up around 0.07 millimeters a day. But then in the middle of winter, it's getting down towards 2 and 1 millimeter per day. So if I'm growing broccoli in winter, I'm really not using that much water. And so the crop evapotranspiration, I multiply my crop coefficients. So you remember the crop coefficient was 0.7 at the beginning of the season? Well, instead of 7, it's a little less than 5 now. So that's and that's meters, but it's 5 millimeters. Okay, so this is my crop evapotranspiration where after I multiplied times the crop coefficient. Okay. And so with that reduced amount of evapotranspiration, I had to decrease my irrigations. I was putting on like 10 centimeters a day or 1 centimeter a day, 10 millimeters a day. So I decreased my irrigations. I put them like farther apart. And So I didn't really look carefully if I wasted water, but I would if I was putting, I will actually. Actually, I'm just going to use the irrigations from our experiment. Okay, so um, so anyway, I put in some irrigations, just like we put in irrigations on that qualifying exam for the aquacrop model. This is basically the same as aquacrop. Aquacrop's better, but we're doing basically the same thing as aquacrop. We're keeping track of water in layers, we're adding irrigation, we're keeping track of the evapotranspiration, just the same. Okay, then I had to do my root depth. And what's often done with roots is you say the roots follow the crop coefficient curve, okay? So with our modeling, we usually start with our roots 40 centimeters deep. And the idea behind that is the roots are going to grow down to 40 centimeters anyway. But if I was trying to agree with like a sensor in the ground, which I'm going to be trying to agree, I would start them at 10 centimeters and let them grow down. So, because I wouldn't want to say that my roots were extracting water from the second layer to start with. I would want to be more accurate. But typically with this kind of modeling, you just say the roots are starting at 40 centimeters and you don't worry about what's happening in the very early season. So again, it's the segmented curve. So we start with our initial root depth, and then we look where we are on the curve, and then we calculate either based on a interpolation function. And we don't have an end season phase because the roots, unless it's like a 2-season crop like Waiuli or something, we just say that the roots grow to the maximum depth and then they stay there. Okay. Then um I had to adjust my fractions of uptake in each layer. So I have this root fracs function where I put in the number of layers, I put in the depth of something, not sure what, s dot depth. Oh, s dot depth, that's the depth of each layer. That's an array. Okay, so that's from the soils file, soil array file. And then I'm sending in an array. Here's the root depth at this I. So here's I from 1 to t num days. And then here's the fractions of ET that are coming from each layer, defined as if the roots were the whole way down. So that's from the soils file, soil spreadsheet also. So I've sent this into this function, and then I check to see where is the root depth layer. And so I say if the root depth is greater than depths at j-1. So notice I don't have to name the same, I don't have to have the same names, okay? These are just in the same order. So here's root depth here. This is c dot root. So the crop file, the root depth on that day. And I had to remember I defined that. I calculated that inside my class, my crop class, my root depth per day. And so I put this into my this root fracs function. It looks to see which layer it's in. It sums up the fractions like 0.4 plus 0.3. So let's say it's in layer 2, it's 0.4 plus 0.3, which would be 0.7. And then I take my frac is my full fracs divided by my sum frac. So sorry about that. I tried to turn my phone off. So it rings when I don't want it to ring, and I can't say anything into it or hear anything when I'm trying to talk. So it's a really great device right now. Randomly, it'll work. Like my son called yesterday, it worked for that. Thank goodness. I didn't even know he was coming into town. But anyway, so the frac is the full frac, like 0.4 divided by 0.7. So that'll, if I take 0.4 divided by 0.7 and 0.3 divided by 0.7, that'll sum to 1. So that'll take all my water out of my top 2 layers. So that's what that's doing. So now, you can see that for the first part of the growing season, until the roots get into layer 3, all my water is coming out of my top 2 layers. And then my water starts coming out of my 3rd layer when it gets into the 3rd layer. And then my water starts coming out of my 4th layer when it gets into the 4th layer. And also the reason, remember I said the reason the broccoli crop coefficient is so high is I think they're so when they germinate these crops, like in Yuma especially, they put out these sprinklers on aluminum hand lines and they water them every day because they can't afford to have any crust on the soil surface because the seeds won't get through. So they water the surface every day. And so that's what this is supposed to represent, this everyday watering. It's not really every day, it's every other day, but if I watered every day, the lines wouldn't go down. So I watered every other day. And then, okay, so we've got a couple of normal irrigations after the germination. And the water's going down to about 0.17 from 0.2. And so remember, we talked about management allowable depletion. So if management allowable depletion for broccoli is like 30%, this would be MAD 30% because we're going down to 0.17. And I said in the tipping bucket spreadsheet that permanent wilting point is 10% and field capacity is 20%. So if our MAD is 30%, that means we'd be irrigating between 17% and 20%, or 0.17 and 0.2. Okay, so I think I have a pretty reasonable irrigation schedule. Not sure, but you know, we're not using much water here, so we don't have to water very often. I'm probably watering too much, putting too much on, because this means I'm bringing it back up to field capacity, but I'm probably putting on more and leaching because we wouldn't see that in this little model here. Okay, and then here's the salinity for the same situation. So you can see we're keeping our salinity pretty low. I can't remember, but we had a problem with salinity at Maricopa recently. I can't remember if it was broccoli or cantaloupes, but you do have to be pretty careful with salinity, especially with drip irrigation, because the drip doesn't tend to wash it out of the soil. The flood irrigation washes it out of the soil, but the drip maybe pushes it outward. Okay, let's move on to nitrogen. So now we have the same sort of movement of nitrogen. Remember, nitrogen is a salt, nitrate. So we've got a mobile salt dissolved in the irrigation water. It'll move from layer to layer. But we also have other processes going on. So we have fertilization, we have mineralization, nitrification, plant uptake. So we've got to add those in. And remember last time I divided by water content to get the DN? Well, now I don't want to do that. I want to know the total mass of nitrogen that I'm adding to the soil with these different processes. And remember, one unit to use for that is kilograms per hectare, but we are using this kind of goofy units, milligrams per liter times meters. That's our units. Okay. Just because we have our layers in meters, and so we multiply that times the milligrams per liter in each layer, and that gives us our amount. Okay, so and I'll go over these individually, but we have different algorithms for our fertilization. We need to know our average depth, because that governs the mineralization denitrification rate. So before we just had the thickness of the layer, now we have the average depth of the layer. Then we have 3 different fertilization times. I'll talk about that. And then we have our change, and this is in mass now, it's not concentration, mass per unit area, mineralization, denitrification plant, and then we add them all together, and we just add it at the very end of the numerator. Here, remember, this is the same as our salinity numerator, except instead of EC, now we have nitrogen. And so the only thing we've changed really is added DN. Okay, so are there any questions? All right. So here's our fertilizations. This is in the crop file. And so I think October 1st is like day 275. So we're going to apply a fertilizer application on day 293 after we've finished with all those sprinklers, irrigations. And then we're going to apply another fertilizer application on day 338. And then this says 230, but this isn't within my broccoli growing season. So 230 would be like August. And then we're going to put on 50 kilograms per hectare on both of those days. So I have for application 1, rate of application 1. So, and also we're applying our fertilizer to the upper layer. So we say if J equals 1, that's the upper layer, J. And the fertilizer day of year, these are in day of years, not days after planting, equals our daily dot day of year. That's why I needed to add a day of year column to that spreadsheet. Then I'm fertilizing. And I don't need to know the thickness of the layer because all I really care about is the kilograms per hectare, and I'm just going to convert that to milligrams per liter times meters. So I'm checking for my 3 fertilizations to see if they happen on that day. And here you can see that M fer, the fertilizer, is just application rate divided by 10. So here it is. I have the dissolution rate in here, but and I'm gonna need to adjust that a little bit but I'm just assuming the dissolution rate is 1, it all dissolves the first day I fertilize. But if it didn't, I'd have to change that. So I'm just returning the mass of fertilization. Okay, then for the mineralization and denitrification, I need to know the temperature. And so the temperature of soil varies a lot during the day, but I'm not going to worry about that this time. I'm just going to worry about the average temperature as a function of day of year. And so this is the temperature follows a sine curve. And so what you have in this equation to predict the temperature on any day is you have the average temperature. So that's in this T bar average. A0 is the total variation. And TM is the day where it goes above the average. So like day 130, it gets above the average. So that helps you define your sine curve. So there's an equation in there that calculates based on this TM, day of year that we're on. We are on this curve and what the average temperature is on that day. Okay, so then we can do mineralization. And for the mineralization, we have to calculate it for each layer. So we're going to take the water content on the previous day for that layer. I'm sending it the temp. I need the permanent wilting point, the saturation, the average depth. And it looks like, I'm pretty sure there's an underline there. I just didn't probably copy it right. Get it on the copy. And then DZ, the thickness of the layer. Because now I do need to know the thickness of the layer because I have a change in concentration, but I need to multiply it times the thickness to get the amount. Because what I'm interested in now is the amount going out. So we went through these calculations before for the mineralization, but now I'm just multiplying GM times DZ, and that'll be my change. Remember before we divided by water content because we wanted to know the change in concentration in the water. But now we're not concerned about that. All we're concerned about is the mass. Denitrification is the same. So you can see I have all my function calls together, but the denitrification is this middle one. Basically, it's the same. So we calculate our denitrification. And then what's typically done not always, but one way to, your plant uptake doesn't remain the same the whole year. It varies with, what part of the growing season you're in. Obviously, a little seed isn't going to take up much nitrogen, nor is it going to take up much nitrogen, like say that the crop is drying out. So what I needed to do, or what sometimes is done, is you just say the nitrogen uptake follows the crop coefficient curve. That isn't a very good assumption for broccoli because a lot of this early crop coefficient curve is due to sprinkling up the seeds. But anyway, maybe I would say for the uptake, I would start it at 0.4 or 0.3. But anyway, what you can do is you can add up all the KCBs and then divide each day's KCB by the total KCBs to get the uptake for each day. And so I have a daily frac of uptake, but I also have a layer frac because the plant's taking up different amounts from different layers. So for this plant uptake function, I send it the daily fraction of the total seasonal and the layer fraction versus other layers. So it calculates the plant uptake in each layer. Okay, so here's the summary of everything. We have our DN min, DN denitrification, DN plant. My fertilization was above it. We add them all up together, and that's my total change. And then we add that DN to the end of the equation. And here's the nitrogen graph. So we started around 10. Maybe the bottom one was at 30. And then we had this initial phase, and remember we fertilized right after that. So we brought our concentration in the upper layer up to like 150, but then it gets leached. Remember, nitrate is a negative ion, so it doesn't get absorbed to clay particles. So we leach it, and then it goes into some of the lower layers, and then it actually gets lower here. And typically, for most crops, you say that you want about 30 milligrams per liter in the soil, and they usually look at the top 60 centimeters for that. So we're kind of in that range. And maybe it's 30 centimeters, but I think it's 60. And anyway, you can see that with respect to 30, we're keeping it pretty good here. We're getting kind of low at the end of the season. And so maybe I should have put on like a little bit more nitrogen here, but we're maintaining it about right. And then if you're interested in the date, these are so I planted it on October 1st, and these are my nitrogen concentrations. So we have been keeping track of nitrogen in our experiment. So I'm going to see how this compares with our experiment. Any questions?